Hello, everyone. My name is Jaren Devey. I am the ASI Automotive Development Manager, and I will be presenting on behalf of the Autonomous Solutions Incorporated Automotive Group. What challenges does ADAS testing face? Some of the major problems are as follows. Preliminary testing of the ADAS as a whole is only done in simulation. Testing these extreme scenarios on a real vehicle would not be safe for drivers, nor would they be repeatable with any consistency. Vehicle integration testing solutions include testing only individual components or functionalities. Real-world testing is often done with a safety rider in the vehicle on public roads. This tests some of the functionality of the system, but hopefully would never result in the testing of emergency type scenarios. The problem statement then becomes, ADAS testing often goes directly from simulation or component/functionality testing to testing on public roads. There is a gap in ensuring these vehicles are safe to release on public roads. This presentation will address that gap. To answer these problems and be able to accelerate and produce more reliable testing of the emerging ADAS technologies, ASI Automotive has developed autonomous systems capable of choreographed vehicle control. We call this swarming. Today, we will discuss what swarming is, why it is needed, and what are the results. In order to be able to present this material adequately, a couple key ASI products and features will also need to be described. So we will briefly discuss ASI's command and control software, MOBIUS, as well as the ASI robotic system that interfaces with the vehicle. But first, an overview of swarming. This video shows an OEM vehicle, which is referred to as the host vehicle and is shown as red in this video. The ASI controlled vehicles are referred to as target vehicles and are shown as white. This is a simple example of the host vehicle sensing the target vehicles while the target vehicles are choreographed around the host. This invokes responses from the ADAS sensors. These are real shots of initial testing of swarming with a simulated overview of the test. This first scenario describes a vehicle passing in front of the host vehicle, causing the host vehicle to reduce its speed. The second scenario is definitely one of my favorites. This is like somebody nearly missing their exit and needing to swerve in front of you in order to be able to get there. These scenarios are just two of the several dozen that are already in use, many of which are running 5+ vehicles. So level up your testing. According to the levels of driving automation, we are currently testing at a level of L2+. This means that we are still technically in the driver assist realm, but incorporating a whole new layer on top of the traditional ADAS testing features. Most other ADAS testing is done through simulation, but with our solution, you can export paths from your simulator and import them into MOBIUS to be run on actual vehicles. This will provide you with your desired test atmosphere. Testing higher levels of automation, L3 through L5, will also experience the same gap between testing in simulation and being released for testing on public roads. These levels of automation should be tested using swarm scenarios and vehicles to bridge that gap. Live testing of the complete ADAS platform provides more realistic results than a simulation can produce and is more rigorous than testing individual sensors and components. Swarming scenarios put the test vehicle directly into situations the vehicle could encounter while driving on public roads. With swarming, scenarios can be swapped within seconds, offering more flexibility in testing. This allows for stress testing of the ADAS features. Swarming scenarios are often designed with a specific ADAS feature in mind, or can encompass multiple features in a single run. In these scenarios, the ASI robotic system is used to get the host vehicle posed correctly at a defined position and velocity relative to the target vehicles, and then engages and releases control to the OEM's ADAS. The ASI robotic system regains control of the vehicle at a predefined position on the path after the ADAS test portion of the scenario. ASI also commands control of the system in the case of a failed scenario. The target vehicles utilize the same ASI robotic system to perform their portion of the swarm. This is an overview of the ASI robotic system hardware. We start with our sensors. The sensors collect environmental info and relay it to the onboard VCU, the vehicle control unit, to give awareness to the automation system, compatible with a Mobileye camera system. Swarming, however, does not utilize an obstacle detection system as it tends to interfere with extreme test cases. The control unit is ASI's patented VCU, or Vehicle Control Unit. This computer is the brain in the vehicle. It communicates with the sensors and controls the vehicle. It also relays info between the vehicle server and ASI's command and control software, MOBIUS. These actuators are universal actuators and are placed in the vehicle to communicate with the VCU so that the vehicle operations can be controlled safely and accurately. In by-wire vehicles, no actuators are needed, as the VCU integrates with the vehicle controls directly. In testing ADAS, it is often more desirable to simulate a human driver rather than using the by-wire abilities of the vehicle. The ASI system and robots are OEM and vehicle type agnostic, meaning you can use this system in any make and model. The ASI system is also hardware agnostic, meaning these ASI actuators are not strictly required. As I've already said, drive-by-wire vehicles don't require any additional actuators. ASI robots are professional drivers. These robots are already used in durability and misuse testing across 17 OEM proving grounds, with several more going live this year. They are already taking drivers out of dangerous and harmful situations. Swarming is a natural extension to what these robots are already capable of. Testing ADAS features in any realistic situation requires professional drivers to perform precise and dangerous maneuvers. The ASI robots are the professional drivers needed to ensure safety and accuracy. This is a quick overview of the MOBIUS system. Here, we place a vehicle automation kit, which contains the VCU, the vehicle control unit, into a vehicle. That vehicle is then able to communicate with its sensors and also reach out to the MOBIUS network. MOBIUS sees the vehicle, gets the vehicle information such as the vehicle specs, its location and orientation, and then you can use MOBIUS to command the vehicle to drive to a location on the site map. The vehicle will then drive to that location. This has many uses and is currently being used in several durability, misuse, and ADAS technology situations. Here, I describe the scenario in MOBIUS, a swarm scenario. Here I show the vehicle velocity profile and the acceleration profile for this particular path. I then move over to target 5, which is another path in the swarm scenario, and show its velocity profile. Here, I show the autopilot engage and disengage action points. These can be dragged anywhere along the host path. I then show here a simple time lapse of the scenario. I'll zoom in here, and you can see that the target 5 path passes in front of the host vehicle. This will induce a slowdown on the host vehicle. And for the remainder of this video, I just show the end of the time lapse of the swarm scenario. ASI has mainly up to this point been focused on path following and velocity control. Swarming scenarios are unique in that they require several vehicles be at a specific position and velocity at a given time relative to other vehicles in the swarm. The dark green here in this image shows the vehicle's actual velocity in meters per second. The light green shows the vehicle's desired velocity, also in meters per second. The dark blue shows the longitudinal positional error in meters. The case shown here shows 3 vehicles performing a swarm scenario. The host vehicle, this top plot, was accelerated up to 29 meters per second. Once it reached a specific point on the path, the ASI robot passed control over to the host ADAS, as denoted by this ADAS engagement point. The ADAS ACC speed was targeted for 29 meters per second. The target 1 vehicle then passed in front of the host vehicle while traveling a bit under 27 meters per second. The host ADAS reduced its velocity to maintain the specified following distance. Target 2 continued to drive in its lane at 29 meters per second. Right before the deceleration, the ASI robotic system commanded the ADAS to disengage, as is denoted by this ADAS disengagement line right here in this top graph. Control of the vehicle was then assumed by the ASI robotic system, which then brought all vehicles to a stop according to their swarm scenario paths. A recent study, evaluation of active driving assist systems from May 2022 by AAA, testing multiple L2 ADAS vehicles, found safety concerns with ADAS performance and produced a recommendation that, quote, automakers should focus on refining ADA system performance in the context of edge case scenarios involving other passenger vehicles and VRUs, close quote. Testing extreme ADAS responses requires multiple extreme test scenarios. These tests are complex and virtually impossible for human drivers to perform. This leads to errors and stress, which can all increase the risk of an incident and possible injury. Not only can the ASI robots perform these extreme tests, but they can repeatedly do so without fatigue. ASI robots continually monitor the vehicle's health data, for example, the engine temperature, and can stop or prevent scenarios from running in unsafe conditions. MOBIUS performs pre-planning path checks to only allow valid paths. This ensures no chance of a collision, even at the maximum allowed error conditions. Removing human drivers from the vehicles makes testing the system safer. When vehicles fail their scenario, smart stopping is triggered. Smart stopping enables one or more vehicles in a swarm maneuver to activate a safety stop for all vehicles in the swarm. It utilizes a V2V communication system to allow vehicles in the swarm to make more intelligent decisions about how they come to a stop when the swarm mission does not go according to plan. Each vehicle receives the position and velocity of all the other vehicles collaborating in the swarm. Vehicles modulate their velocities to spread out and avoid collision while they are stopping. Each vehicle may modulate its velocity differently from other vehicles, which is what sets smart stopping apart from traditional escalated stopping behavior. ASI's lateral left-right control algorithm utilizes clothoid path-following techniques to achieve smooth control. Positional components of the path are sent from MOBIUS to the VCU. Using an ASI-developed EKF, the position of the vehicle is estimated and then compared to the path, and a lateral error is determined. The VCU then determines a steer angle to reduce the error. ASI's longitudinal ahead and behind control algorithms consume the velocity, distance, and time trajectories for the swarm scenario. Using the aforementioned EKF, the estimated vehicle position is compared to where it needs to be along the path, and a longitudinal error is determined. The longitudinal controller then determines the optimal throttle and brake commands needed to follow the swarm scenario trajectory. ASI has typically set the default maximum error before an escalated stop is triggered to about 3.5 meters of longitudinal error and 0.7 meters of lateral error. These values can be dynamically changed to account for the planned distance between the vehicles in a scenario. This is an example of a single day's worth of testing swarming on multiple scenarios with multiple vehicles. These histogram plots show the typical accuracy we are achieving consistently. On this day, some vehicles participated in almost every swarm scenario with the host, while others were traded in and out depending on the number of vehicles needed for the scenario. The vehicles tested on this day were a minivan, which is denoted as Vehicle 1, a truck, Vehicle 2, a convertible sports car, Vehicle 3, and the OEM ADAS test vehicle, host vehicle. It should be noticed that the longitudinal error for the host vehicle is higher than for any of the other vehicles. This happens when the vehicle is using ADAS and the response is not the same as was indicated in the simulation used to generate this scenario. The ASI system is continually monitoring the acceptable tolerances for the longitudinal error on the host vehicle, and if this error is too large based on the acceptable distance between vehicles, the ASI system will take control and bring the vehicles to an escalated stop using smart stopping. These histograms are just one simple example of how the data collected from these vehicles can be used to determine correct behavior of the ADAS platform. This data can also be used to determine if the ASI system on a vehicle, hardware, or tuning needs attention. These plots show that Vehicle 3 has an obvious bias towards positive lateral error. In this case, it indicated a bias in the steering robot that wasn't being addressed. Overall, this data shows that the ASI system is keeping the vehicles within half a meter of lateral error and 3 meters of longitudinal error, up to 3 sigma. ASI has determined that swarming is highly aligned with the testing of the following and more features of ADAS. Swarming lets you test all these systems simultaneously in real-world scenarios with real-world vehicles. Adaptive cruise control system, forward collision warning, advanced emergency braking system, blind spot monitoring, adaptive front lighting system, lane departure warning, lane keeping assist system. Since swarming scenarios are designed to trigger a specific response from ADAS, the exact expected time of these triggers is known. If the swarm was successful and the expected trigger did not happen, this is a clear indication of functionality failure of an ADAS component. Some additional features that can help benefit swarming. We have paths. Paths are predefined positional and velocity constrained trajectories for vehicles to drive. They differ from swarming in that they don't require the vehicle be at a specific location at a specific time and are planned on an individual vehicle basis rather than a group of vehicles. Paths can assist in swarming by giving the vehicle a trajectory for how to get to the start location of the swarm scenario from wherever the vehicle currently is. Playlists are a group of paths that can be run in any predefined order. Playlists could benefit swarming by providing a predefined grouping of swarm scenarios to run one right after another, with their connecting paths included. Map editing is a powerful tool MOBIUS provides to be able to define the roads and areas the vehicle needs to stay within. This allows the user to visualize where the swarm scenario will be run. Geofencing is one way that MOBIUS maps provide safety. MOBIUS continually monitors the vehicle's position and determines if the vehicle is approaching the map edge. The ASI system will then either slow down, bring to a stop, or bring all the swarm scenarios to a stop using smart stopping. Robotic Safety Rider is a mode in which the ASI system continually monitors the vehicle's condition, such as position compared to the MOBIUS map, even if the ASI system is not in control of the vehicle. The system will then issue a stop command to the vehicle if the map will be or has been breached, or if other conditions have been met. An example, too large of lateral or longitudinal error. This is essentially what the ASI system is doing on the host vehicle while that vehicle is using ADAS. Customer-generated events. While ASI provides a way to create swarm scenarios, we also support customer-generated scenarios, as we are very aware that customers will have pre-existing software used for the simulation of swarm scenarios. This allows customers to bring their simulations to life. So in conclusion, swarming is already being used constantly to run ADAS production validation paths at OEM facilities. Customers can test in simulation first, then import those paths into MOBIUS and run them live on the track. Multiple ADAS features can be tested in a single scenario using several vehicles. Our software controls the OEM vehicle until the test is ready to start, then seamlessly engages the OEM system and acts as a robotic safety rider. V2V with smart stopping makes escalated stops much safer. Swarming fills the gap between current ADAS testing that uses simulation or component/functionality validation and real-world testing on public roads. Today in this presentation, we have discussed what swarming is, why it is needed, and what are the results. We've also seen that the system is safe. Swarming takes drivers out of dangerous situations, thus increasing safety. We are accurate. The control algorithms create accurate responses. Live testing of ADAS features is more accurate and realistic than component or simulation testing. Repeatable. MOBIUS can be used to determine what swarm scenario to run. Paired with the accurate control algorithms, this creates high repeatability. Fast. MOBIUS can also be used to swap out scenarios within seconds without the need to train drivers on how to perform each scenario. This makes swarming testing undeniably much faster. This is the end of our presentation. Thank you for watching.